Let's get recording. Okay, good morning, students. It's a Pereira's here as well. Mornings. We are continuing with the next installment of Stencil materials, right? Is it installment or next chapter, next section of work? Mornings, Alex. I think I greeted you earlier on. Not sure if you were by your laptop, computer. And we have arguably 3 more chapters. There is buckling at the end, which we will cover. But obviously, the next 3 chapters will focus on your next assessment or your next test, right? So that's worth noting. So once we've obviously you concluded your MOM test, in essence I recommend preparing the next chapter. We have chapter 10, chapter 11, and chapter 13, which is the shear stress in beams and the deflection in beams, and then buckling at the end. Obviously, buckling will be in the final. But anyway, just some announcements to make. Mornings. So this is what I've scheduled thus far. I will share this obviously officially. And you know, I just want to say something before we actually look at these dates, guys. If you're feeling ill, right, please stay home. Obviously don't want what happened last week, because last week, yeah, it really derails all of us, a lot of people's plans and things like that. So anyway, these are the class test 2 dates. Obviously they are on campus. Hopefully we've seen the last of online assessments. And the first test will be strengths, which is on Monday, the 18th. Electros on the following Monday. And then refrigeration on the Wednesday. It's in basically the last week, and then October. I do want to make you aware. Okay, anyway, and then the following week is the quote-unquote study week, and we might use it week also to finish any outstanding content, but there will be that week. And then obviously your final exams is from the 9th to the 26th. So the good news, I've seen the timetable to Mr. Conradi. Well, I prepared our timetable, which is the S4 Marine Engineering timetable. So I have an idea of what we're looking at. And the exams, the only thing I need to change, I want to make the exam time from 10 to 1 instead of 9 till 9 till 12. But I still need to sort it out. Other than that, this is the next phase, the next assessments. Obviously, the weighting, it's also 25% or a few other term mark. All right. Yes. And then the other note, which I want to include here, which was this. Let me just write it here. I will have lectures in between, unfortunately. We will have lectures, right? I should write that here. Lectures in the week. But it's probably like 1 or 2 lectures. But obviously just to pay out the content. Once you just conduct the lectures, obviously it's recorded, so you have it there. So I'm just gonna put that over here. And maybe the reason why I'm just doing that is so that we don't actually run into that other week. That's my plan. Are there any questions regarding this before we move on? Before we get into the theory of bending? Students, let's engage Musa. Mornings, Jason, Takifa.
Yeah, the plane looks good.
Thank you, Silas. Thank you. Morning, Musa. So yeah, like I said, I would share the dates. No questions. Okay. Yeah. Guys, don't have a lot of anxiety. With regards to, I not have a lot of anxiety, but you must believe in your hard work, you know, and I've set it everything in a way. Um, you know, you watch my lectures, it encompasses all the stuff that you kind of need to solve. So yeah. And I think it's challenging enough. So you don't have to. We'll have classes, yeah. Or whatever you've been doing, just keep, for the guys who knows my flow, you just keep along. I don't know, a lot of students, I don't know if they battle all the content, which I don't really understand why, but you have to keep up the work. Consistency, you cannot bulk session the stuff. The stuff will kill you. You can't overnight. You need to keep up. Like I said, you need 3 to 4 hours a day just to keep up. It's a lot of content. We are all pushing around 6 times 4, 24 different sections of work, each with its own complexity. Some are easy, some are not aligned properly. So we're at the second stretch now, and I recommend just keeping the momentum. Obviously, you're going to have this weekend now, which you should enjoy probably. But just keep the momentum. It's not difficult. Yeah. I mean, I've passed it. I'm sure it's not difficult. It's just a lot of content. You just got to manage your time, and you should be good. Worst comes to us, you get a 50%. Mr. Trele, Mr. Mtambo, mornings. Okay, so yeah, so this is what it is. The exam timetable will come out. I don't want to share the draft before. And once I receive it, obviously I'll inform you before the time. Fortunately, don't have any test dates for what's the subject now? For MEKs or subjects. Hi, Mr. Mtambo. Please don't ask me a question which I already stated before. What is it? Mr. Mtambo, you got a question? Oh, so now you. So 10 early. Okay, so there's nothing else. I think maybe I should just gooi this in here. Gooi it in. I'll have it over here while I'm here. What is this? Is a scope. So bending, shear stress, shear stress, shear stress. Section beams, right? For electrodes, we're going with sync motors, sync and induction motors. This will be shared. I'm pretty sure I'll ensure that I share this. Transformers. It might just be this 3 and then transmission lines. Have a look here. I'm going to say something. And testing. No. I don't cover the testing chapter, Mr. Kasser. That's a theory section, right? And you know what is so sad about that chapter is that, you know, I've literally done. I can't cover that chapter. If I were to cover that chapter, I would have taken you back to Mechanics to the labs. I can't. It's just like, just not part. We don't have time for that. And the nice part about the chapter is because I worked in that field. I will give you the best stuff ever. Promise you. I would have given you not the best, but I mean, obviously, I'm experienced in that field, so it's like the most proper thing ever.
And the reason why I asked,
go for it.
Is you recently said a while ago before test 1 that test 2 would be chapter 10, 11, 13, 12. And 14, or
yeah,
and then chapter 15 will be in the exam.
So I think I made a mistake. I think I meant chapter 10, 11, 14, and then 15. 15 was in the exam now.
So test 2 will be 10, 11, 14.
Yeah, that's correct. Yeah. Sorry about that. I see. You're correct, yeah. Should I have it in brackets here? 10, 11, 14. Okay. That's great. Why did that happen? Okay. Yeah, because these what do you call it? These sections are like a trilogy, man. Yeah, and buckling's on its own. Okay. Yeah, so that's one. There's no real chapters here, so this is like arguably 4 sections. For this, we're doing refrigeration section, heat transfer I'm doing after that, air compressors. Right. Okay. So that's that. If you do want to study it, just ask me. Somehow Alex does always ask me. Just that it's a bit tricky sometimes, depending on how I get the content. Heat engines. This will be. Yeah, that's too long to write, but I'm gonna say. It's gonna be chapter. Where's my theory of machines book? Just give me a moment. Yeah. I have to just repost this. So chapter 15, 16, 15. And I wonder if I will get to gearing, but I'm just like, I have to see, but it might just be those two with gearing, or just gearing. The thing is, ideally you want to hit around seven chapters. But it depends, obviously. 6 to 7 chapters a subject. I'm just looking for gearing. I don't know why I'm passing it. I'm just looking at gearing. In fact, gearing comes with the other part, but it's just so tight. Especially when obviously one spends time in chapter 12. It stands this. Most definitely probably this, yeah. There's normally one chapter outstanding for the final. I hope that's clear to everyone. You guys get that? Let's have it over here. I think Alex likes structure, man. Doesn't like. What are you talking about for which subject?
You said there was a chapter outstanding.
No, man. That's for all my subjects. I mean, like, we have one more chapter before the final.
Oh, okay.
Does it make sense? It's outstanding. One chapter will be covered before the time. Covered for final. Normally. Yeah, okay. So yeah, so like for instance, buckling will be covered for the final, which will be covered in the final. Transmission lines, no, in electrodes is no chapter like that. For thermos, there could be. There might be engine performing and testing, which is the easier section. And for heat engines, there might not be as well. It just really depends on a lot of factors. Yeah, but it's the comprehensive bit of work. I think I'm glad I actually just did now. So obviously we'll share this again. And I think with date and time, we're just gonna work on it now. Obviously I always give enough time. Shouldn't be a problem. Will be the same. Always 2 hours, 30 minutes. So that there's no excuses. I have enough time to sort that out. Okay. If there's no more questions, I'll just proceed now on the actual lecture now. So can I move on, students? Just give a few thumbs up there. Thank you. Thank you. Can I get some more? Morning, Mr. Boyd.
Go ahead.
Oh, fantastic. All right, guys, where are we? So in Standard Materials 2, we started off with, okay, before I think I'm jumping the gun. So remember I've mentioned to you there is essentially 5 mechanical types, these 5 different types of loads in Meki, right? And well, I'll just ignore the one on the buckling side. Of course, that's the main loads. We also get I guess, all the secondary loads, which I call it primary, secondary being, you know, internal pressure due to fluid, like internal vessels, or temperature was another form of loading, right? But obviously, I tried to unpack all the main ones. So we've done a bit of tension, yes. Arguably done a bit of compression, which is the same as right, so we've done a bit of tension compression. You could say the sister and brother, right? They roughly behave the same for steels. We've got a shear force, which I did cover well this time around, not like last year. I actually spent a lot of time on looking at shear force, making sure you understand the area, if you remember your area and perimeter. And of course, on the shearing concept, you kind of went into torsion, right? And you know, yeah, I'm thinking here. So torsion would be the twisting force. We covered a whole chapter on that. That is chapter 4 in your textbook, if I remember right. And now we're finally moving on to bending, and that's the 5th mechanical load. So once you've completed this course or subject, module of strength of materials, you've gotten a good like primer, you know, or fundament of all the different types of loads. Of course, it does get always more complex. So what we're looking at now is bending, and obviously bending we talked about in the previous chapter, to do the second moment of area, if you remember, and I had a talk around that where bending is where the second moment of area is a very important property or geometrical property of an object. Right, so today we unpack bending 1, 2, 3, number 4, number 5. Right, eventually we'll unpack buckling, but buckling is not another load, it's a compressive load, it's another form of condition. I don't know why it's here, nevertheless. Okay, so just reading off in the actual chapter, introductions, or says shear force and bending moments will be induced in beams subjected to transverse loads. Okay, so before we start, chapter 6 is heavily incorporated within this chapter, right? So if you are battling with chapter 6, you need to go make sure you go back and go revise now. Chapter 6, the shear force and bending moment chapter, right? If you're wondering why, I always wondered why as a student, why do we do shear force and bending moments? Like, it's not being told, you know, why are we just drawing these diagrams, you know? Rest assured, I will make sure you understand why. So yeah, so just reading back in the text there, it says, in addition, there will be axial ply loads to the beam subjected to. So when we're talking transverse loads meaning the loads as you can see there, right? So it's applied on top of the beam transversely, and then also we have limbs loads which can be applied actually to the beam as well. So that's to the cross section of the beam, and both of those forces, right? Well, it doesn't have to be the cross section of the beam, but actually both of these forces cause stresses in the beam, and those stresses are caused by the bending moment term bending stresses. So yeah, so that bending moment, right? So remember we talked about different loads, like so tension and compression, that induces direct stresses in the form of tension or compression. We've got shear stresses, which is induced by torsion and your shearing, and of course bending as well. That it's bending stresses, but it's also in form of, yeah, we'll unpack that here. So now let's say, this is a very important thing in designs of beams anyway. It says in beams where the span is relatively long, the bending stress will be large compared to the stress induced shear forces and the axial load, if any, and hence only bending stresses normally influence the selection of a suitable beam section, which you unpack. So what's important to note, if you at a desk, right, and I unfortunately never, if I could show you, if you zoom your ruler, for instance, and you fix one end of your ruler, but let's say you fix only like around 10 more, and you apply load on the tip of that of your ruler, and of course you're fixing it on the one end, you notice a considerable amount of bending of the ruler, right? And normally beams, depending obviously how long they are, they're most likely to fail by bending and not by shear. I have a shorter beam, so a shorter beam, if you instead of showing exposing the longer end, flip it around and have only like around 10 more exposed, not 10 more, but maybe a bit more, maybe 20, 30 more. And grip the whole other end of the ruler on the other side and start to apply a force downwards. Shorter beams normally fail by shear, right? So what they're basically essentially talking to here is that bending stresses takes majority of the forces within the beam. Shear stresses are important, which I'll unpack in the next chapter, because with shear forces we end up with horizontal shear forces, and when you join the beams, that could actually one needs to design for it as well, but that's what's important. So when you're designing a beam, particularly a beam, and when I'm saying a beam, right, this is also I'm talking about shafts, anything which is supported like a beam, right? So a shaft is a beam, your prop shaft is a beam supported by bearings along the way. It's same kind of I guess analysis or thought or engineering behind what's happening here. So yeah, so that is just that, right? So that's where we're heading into. That's just a beam with transverse loads basically on there. Okay, just some examples, some basic examples. This is what I've mentioned. Obviously, I've particularly touched on. I've just accentuated the marine applications here, but obviously beams are all over. Maybe I should actually just get a picture here. I guess beams, all buildings are. Oh yes. Sitting last night thinking about I'll include them, but I actually just don't anyway. Like basically, do you guys know the difference between a beam and a girder, by the way? Who's aware? So I'm gonna just make a separate slide here. I'm just gonna really just paste a lot of pictures. Does anyone know the difference between a beam and a girder? Is anyone aware? Just checking. Copy this guy. Guess no one aware. So guys, we're boarding a bridge. We've got these I-beams over here. That's a beam. I'm gonna look for a few more. I mean, every boarding literally has beams, right? I'm gonna go with this one as well. So remember, if you remember, I told you a structure is composed of different structural elements, where truss is one element and beam. So you can see beams running across here. Obviously that's a truss over there. So there's a beam again. Oh, what's this is? Go ahead. Oh, size, main difference. Yes, it's that. Yes, obviously girders are longer, beams are shorter. But I just said it's fantastic video. Essentially, you could say a girder is a beam, but a beam is not a girder. So I'm just looking at some quick stuff over here. I'm nearly done. Anyway, I don't want to unpack too much of it. But I mean, I'm sure you guys have seen beams. Okay, I'll just choose this one over here. Maybe it's more wood. I don't want some wood. It's on the beam, the girder thing now quickly. So yeah, so as an engineer, obviously as marine engineers or mechanical engineers, it's just something we really do. It's really left our trade. But marine or mechanical engineers used to be used to be, what is this? Responsible structures. So before I get into the beam together, I'm going to unpack that again. I just want to really unpack the applications, just to really open your mind further on what a beam could be. So obviously, you've got a vessel, and and even when I think obviously in nav arc, I don't know if you guys have covered shear force in bending moments, and the water will induce a shear force in bending moments, right? And of course, even with your analysis within in your prop shaft or even shafts in general, and this is one of the chapters I wanted to include. Um, it was actually after the deflectional beams, but it's basically shaft design, and obviously because you don't have the time for it, and that's the problem. And within shaft design, you basically it's the shafts are basically subject to combined bending and twisting, or basic bending and torque, and you basically do an analysis in both the X and the Y. You take a resultant of the two, and from that you're able to use two formulas. I think it's the Guest-Tresca, and there's another one. And from those formulas, you can decide on what shaft you choose. So with beams, I guess that's also a structural element, but my point is beams are all over, right? And the analysis in beams, what we're doing is what we're touching on is the core concept of a beam. Okay, so moving away just from the basic applications to where we need to be. So yeah, we just go into an explanation, and one is to just imagine what's happening here, right? So you can take, if you have a 30 centimeter ruler, fantastic. But you should have one now. To the moms, and what is happening here. So I'm just going to explain something, a very important concept, which obviously be highlighted throughout the lecture, and obviously our examples and numerical examples will also, I guess, accentuate that. So if a length of the beam is acted upon a constant bending moment, so I don't worry too much about that, but it's gradually applied, and it's basically before the elastic zone, and they say the stress set up in any cross section must constitute of a couple equal and of opposite bending moment. Okay, fine, no big deal. So we just have a constant bending moment here. And then what's important to note, so if you take a ruler and you bend it, I'm saying here, hence it can be deduced that one part of the cross section is in tension while the other part is in compression. Now this is a very important part to understand. So as you bend the ruler, right, or you can look at this beam over here, right, so it's simply supported, and as you're bending the beam, you notice that the top part of the beam is being compressed, right? So there's two arrows pointing that way. So if you actually do it, you would see it, it's actually decreasing in length. Whereas the bottom part of the beam, that's in tension, right? So the top fiber in this case is compression, and the bottom fiber is in tension. So I don't know if you guys can see that. And I say it is clear that for initially straight beam, from the inside edge will be in compression and the outside in tension. Obviously, we're assuming you're applying the load downwards. If we had to apply the uniform load, you can see there the UDL from the bottom up. The top would have been in compression, and the bottom would have been in compression, right? And I want to be aware of that. So then also they say there will be an intermediate surface where the stress will be zero, and that is called the neutral axis. So always just remember there's something called the neutral axis. Normally this passes through the centroidal axis of the beam, right? And of course, that's the centroid of the beam. So does everyone get the point? If you load a beam, right, in this case, this example over here, you're going to find that the bottom side, the bottom fiber, we call it, is in tension, and the top fiber is in compression. Do we all get that? Does it all make sense to you?
Yes, sir, it's clear.
Okay. Anyone else? Obviously, something besides a bit of experience here. So very important concept to understand, because you'll be tasked to draw stress distributions. Anyone else? Okay. Just believe me for now. That's okay. I accept. Oh, so another example of this. This is one of the pictures I just pasted like a sentence just this morning. But think about a staircase, right? So a staircase is supported at two ends. And as we walk across the staircase, which is some loading, what do we actually do to this staircase? At the bottom part of the staircase, that becomes in tension, arguably in the lower fiber, right? In the upper fiber, you find that the stair is being compressed. So one must really, this, when I looked at this picture, like, oh, it opened my mind up to realize that beams were everywhere, and the stuff that we're learning is really not general, but core concepts of any structure. And as we load the structure, this is what's actually happening to the structure. So I found this very interesting. And what this also means, in terms of analysis point of view, is that if you're aware of what kind of loading conditions is induced within whatever member you're doing, that's the kind of analysis or design you need to do in order to make sure that it remains structurally integrated for whatever amount of time you want. Obviously, with our tenderpreneurs here, we don't really care about such stuff. We just take the money and enjoy. But I mean, obviously, if you're a man who's into engineering and want to see the country move forward and want to do the right thing, those are the things you want to think about, right? So when you have a staircase, even the staircase itself has its own set of design. Obviously, there's nothing to really recover. But what's important to note is that even those loading conditions are considered. So that's a special thing. Okay, so rushing into the analysis, not taking too much time on it. I guess I'm just really explaining what bending is, or beam bending, of course, what we're looking. So I just want to touch on all the assumptions here, just in case anyone wants to get fancy. We assume that the beam is initially straightened and stressed, right? So it's straight, perfectly straight. It's unused, just came off the shelf, perfectly manufactured. Here comes the point 2. We say the material of the beam is perfectly homogeneous and isotropic. That means the properties are the same in all directions. Obviously, this is not true. The elastic limit is nowhere exceeded. Yep, I just mentioned that just now. Young modulus is the same for the material, and same intensity and compression. Yes, one must be cognizant of. This is not always the case. You normally have higher modulus of elasticities in compression, but it's not that much. But it depends, obviously. Let's say the plane cross sections remain the same before and after bending. The deflections are small. They're saying every cross section of the beam is symmetrical about the plane of bending. There's also the loads to which a beam is subjected is gradually applied. So a lot of assumptions we make in this analysis to understand bending, right? So just be cognizant of that. That don't think you're a specialist by any means. However, just know this is a good standpoint for you to grasp the concepts of bending. Okay, so what's really happening here? I'll just quickly, I have to now just push in my graphics tablet here, and I'll show you. But I don't spend too much time on deriving this formulas, but for this one, it's not really, it's not that long, but I just want to quickly show you the idea of where it came from. And I hope you can, obviously now, just get an idea. Obviously, I don't expect you to derive these formulas, so it's good. But I do expect you just to obviously have a good understanding. So when you do solve the problems, you're not completely lost. Okay, so I was here, and what's happening here is basically, essentially. I need new words in my vocabulary. They're not plugged in. They are plugged in. Just give me a moment. I can't. Oh. Just give me a moment. Just trying to find my mouse. And I was gonna use my graphic so for the weekend so long. Because I'm touching it, it's moving away for some reason. Okay, here we go. That's quite strange. Okay, so just give me a moment here. I think okay, yeah. So what is easier, this is was something's different here. Something is very different. I'm not sure what it is. Just give me a moment quickly. Let me just insert the shape rather. Insert the shape. I'll just make it a perfect. I'll make this kind of. Yeah. So if you imagine this shape over here, on this blue one. And what happens is we apply a bending moment across the shape, and I can just make this red now. Just make it thicker, make it red. I don't know why this is doing this now all of a sudden. So we apply a bending moment like this, some kind of moment, and we get the shape you see on your left hand side here, right? Okay, so what happens is now, I did mention to you there's a point of no stress, which is the neutral axis, right? And what we do, we create this imaginary center. I can't see the cursor, see, that's why I'm confused. Oh, flip, my keys are already set and everything. It's quite strange. Let's see, okay, I want to sort this out, guys. It's very weird. So there's an imaginary center over here, somewhere over here, and what we're basically doing here is that we yeah, nothing has changed. I can feel it's not the same. Anyway, so what you call the center of curvature, and then obviously we have something called the radius of curvature here, right? So this is basically using your math one, if you remember, your radian measure chapter, if you guys call it S equals R times omega. Oh, this is really weird. And from this, to say, okay, from the diagram, it can be seen that the length has been stretched. So the strain at Y, and then, yeah, so basically, initially we had obviously this length over here, right? Oh, it's really strange, guys. I don't understand how I feel here. This length, and as we bend this thing, that has obviously increased, right? The circumference of that piece. Now it's called the circumference now, the perimeter of that piece has definitely increased. So that's the change in length there, right? So obviously, if you subtract those two divided by the original length, you're going to get something called the strain. And what they're saying here is that your strain, so if you remember, S equals R times omega, you'll feel like it's something. And as you can see, initially the radius here, if you compare this, the radius was R, and then obviously have R plus Y, which is more deflection. They assume small angles, and you end up with Y equal Y over R, which is that radius. But also we know that stress is equal to, this feels weird, over E, and essentially that's just substitute the strain into this formula over here, and then you have this new relationship here, stress equals E over RY, right? So to say here, from this is apparent that E over R is constant for any bending moment. Stress is directly proportional to the distance of the neutral axis. Very important, very, very important. You could have not known this without the analysis. Okay, let me just get back here. Like that, red. 1 minute. Okay, so red, yep. And they say therefore, in interest of both weight reduction economy material, it's concentrated. Yeah, so this is, I was going to say that actually. So based on the second point is that one must be cognizant of the fact that what we always want is that we want to concentrate the material as far away as possible from the neutral axis. Please remember this. There might be an extra 2 marks for you, understanding what this is. And I say hence the universal adoption of the I-section steel girders, right, or beams. Okay, so if you ever wondered why I was chosen, it's probably due to this equation here, right? So stress is directly proportional to the neutral axis. Increase the stress, the greater the neutral axis, the greater the stress induced. Okay, so just touching from that, so that once again just using basic integration, and we know that force equals stress over area, and then what they're taking is a infinitesimally small area, and they're basically okay, yeah, so it's, and then basically the stress part, they are substituting the stress part with E over RY, And then you get E and R is obviously constant, as we said, for any embedding moment. And then we integrate that. And once you integrate that, we get something beautiful, and that is root y squared dA. And if you remember the actual definition of a second moment of area, y squared dA is called the second moment of area, and basically we result that the moment is equal to E over R I, and that I is the second moment of area. That's why we know that's an important property. If we take all those three equations and basically make them equal to each other, you get the formula that you need to know. It's nearly the same as a torsional formula, which is that one over there on top, right? And it's the moment divided by your second moment of area that equals your stress from at a distance from the neutral axis. Obviously, we talk about that divided by y, which is your neutral axis, right? Equals E divided by R. Just to make you aware, we normally use the M over I equals stress over Y in our analysis versus the E over R. It's very seldom, very seldom, like probably 2% chance you ever see that. So that's a new formula. M over I is like a torsion formula, right? So let's start the torsion guy over here. I'm just disappointed in my graphics tablet. I don't know what's going on. So torque over J, right? Just feels so different. So stress over R, right? Equals, yes. Go for it.
So that I, is that only with respect to one axis or to both axes, so X and Y?
One axis, yeah. One axis, yeah. Depends on the way, depends where you're bending.
Oh, okay.
Yeah, so if you're bending on the X, we use the X, I, X, X. If you're bending on the Y, I, Y, Y. And then for this guy, yeah, we get G theta over L. So can you see torque is a load induced, moment's load induced. I is a second moment property, J is a second moment property. Shear stress, right? R, that is going to be obviously the radius. It's nearly the same as that. Of course, R is important. R also tells us if you remember the stress distribution through a shaft. It's greater at the ends compared to the inner side. That's why we top the hollow shaft kind of thing. You have E, which is analogous to G, and obviously the theta and L will be analogous to the R. So nearly the same kind of stuff here, you know, so the same kind of thought behind, so same kind of thought was actually put in developing the moment formula. So yeah, so that is the formula you need to know, you must know. It's now getting away around it. But anyway, so once we have that formula, and we take that formula and now we start to apply it, right, to a beam. So again, we assume a simply supported beam. I'm enjoying talking so much. It's a bit of a problem, you know. But anyway, hope you guys appreciate it. So we have a beam, apply force in the middle, and as you can see, we at the bottom it's a tensile stress, and at the top is compressive, right? So we have the neutral axis. So guys, can you see on this particular figure here, right? Position entlang the Probenlange. That's probably German. All right? Position along the sample length. Position entlang. I can't speak German. I'm just trying. I'm trying to make that accent. So for this nice square beam, do you notice that? Can you see that the blue line's going the other way? It's compressive, and other side is going tensile. Do you guys see that? And one could say this varies linearly, right, across the beam, across the cross section of the beam. You guys see that? I don't know if you guys are there, right? Morning, Mr. Doyle. Morning, Megan, Mr. Mutau, and Mughal. Mornings. And yeah, so touching on that now. So now it says it is evident that the material near the neutral axis is always subjective to low stresses compared to areas away removed from the axis. Yes, right. So in order to obtain the maximum resistance to bending, it is advised to use sections of large areas as far away from the new tracks as possible, right? So for these reasons, but that doesn't kind of make sense to me. But anyway, for these reasons, I or T sections find favor in present engineering applications, such as girders, where bending plays a large part, right? A very long beam. And such beams have large moments of area about one axis, provided to ensure that bending takes place about one axis, which they'll have high resistance to bending. So that's why your IX and IY would different, obviously that. So just back to the beam and the girder, I wanted to talk about that briefly, but I want to unpack it, and I just obviously don't unpack it now because it might take some time. But it's a comparison chart, and I just want to show you an example quickly. So if anyone does ask you, you have an idea what a beam and a girder is. So we start touching on the concept of stress distribution, but this is like a small lesson in between. So there's a difference between a beam and a girder, which I'll probably have on a separate slide sometime. And I just want to show you an image then, and then I'm basically done. I'll just talk to the image and tell you what it is. It's nothing really important. I'm looking for like yeah, one of these sketches here. Okay, cool. Yeah. So this is perfect. This is perfect. This is perfect. Okay, floor beam. Okay, I'll just copy those two. So I'll just title this beam and girder. Yep. Okay, obviously, other concepts I probably should have touched on as well was like your flange and your webs in I-beams. There's some basic terminology which is not really mentioned a lot of. It's not really mentioned here. It doesn't really teach you about it. But anyway, so I'm just gonna make this bigger. So what it really is when we're talking about a beam is this obvious picture here is let's say it spans between. Okay, so here are the beams are running. I'm gonna say vertical. No, not vertical. So here are the beams here, right? Oh, sorry, the beams are like this. And no, this is not right. The beams are running across this way. I don't know if you guys can see it. Let me just stick my pin in here. Longitudinally. Yeah, I want to say longitudinally, but I don't know why. Yeah, so let's say longitudinally. Yeah, it's running like this. These are the beams, right? I need to sort my pen out. It's really making me feel uncomfortable. So like that. Those are beams, right? So what do they say? So they say beams are horizontal members, and one of the most commonly designed structures. I'm not looking for that. Yes, this is what it. So they say beams are normally intended to carry distributed loads such as parallel walls or tributary areas of the floor and roof systems, right? They say it's basically used for residential projects like buildings, doors, tall standing structures. Not really important to me now, but a girder is a beam laying horizontally, right? So we can say horizontally, and it carries each of those beams as a so-called point load. So you could imagine a girder being like that, and then there's different point loads over here, just like that. So that's what the difference really is. And girders are obviously more long, but it kind of supports those beams in a form of as a point load. And let's say girders support smaller beams and acts as the main horizontal support. Yeah, well, yeah. So you would say it's a cast right. You can call that longitudinally. It's also designed to support major concentration loads such as columns or beam reactions. And they say I-beams are normally used. Obviously, and all girders can be called beams, and they say all beams can be called girders. Yeah, I always remember that one. But anyway, that's just the difference. So this floor beam here is a girder, but even though it's a beam, it's a girder. So it's supporting all these other small beams, and then obviously we have the beams over here running longitudinally. Instead the horizontal members. But anyway, yeah. So that's the difference between the two, right? As a side note. So back to this distribution, right? So we're aware that how we want certain things. So what we're looking at here, I'll start off with this one instead. Is this is your I section over here, and this is a symmetrical section here, right? And when you have a symmetrical section, really I'm talking a lot. How far am I from the actual stuff here? Hey. No, okay, no, I need to move. Is that as you bend the beam, right? Right. Assuming the bending moment is applied, so this is going to be a tensile. Is it a tensile here? Do we call that? Okay, we can call it compressive over here as well. But normally compressive is this way here. It's the negative side, right? And this is tensile. So maybe our beam is being bent the other way. And what we have with symmetrical sections, we have symmetrical bending, right? Which is kind of ideal. And of course, the sections, if you fold them over in this way, they're symmetrical. And when you have an unsymmetrical section, you can see over here, we have, this makes sense here, you obviously bending downwards here, and your stress distribution is at the bottom, that's tensile at the bottom and compressive at the top. But what's important to note between the two is that, as you can see here, they are equal in magnitude and difference in sense. So this is 100 over here, that guy's also 200 over here. That's the symmetrical section. And when you work onto a unsymmetrical section, obviously across this axis over here, you can see that the bottom part of this beam carries most of the stress. So this could obviously be, let's say 300, and this could maybe just be like 150, arguably half for T section. So again, you must be aware, I think the next slide just basically talk to this. And it just states that in the general form of distribution shown the figure 710 below, is figure below, shown the figure below, and saying would occur in any beam having a section center axis equidistant from the top and the bottom, so they're equal distances from the top to the bottom. For such case, the magnitude of the maximum compressive stress would equal the maximum. So as you can see on this distribution, this is what I was starting to look at, this like compressive going the left and tensile right, that the distribution is the same, right? And obviously at the neutral axis, there's no stress. No stress would probably be a good place to join our beam. If you look at an unsymmetrical section like this T section over here, so obviously your centroid's a bit arguably higher up from the bottom, depending on the way you look, and you're going to tend to find that your maximum stress occurs at the bottom. That's a tensile stress there, and a small amount, your minimum at the top. Well, yeah, max. Oh, it depends on where you're obviously looking. So let's say if the centroidal axis of the section is not the same distance on the top and bottom, the stress distribution would still occur, but stress at the neutral axis would be zero. Still, the stress would be very linear from the distance from the neutral axis. Now, the maximum stress at the bottom of the section, and the reason why it's because it's further away from the neutral axis. So the further we are, greater the stress. We did mention that. So that's just stress distribution. Moreover, we got another special property called the section modulus, which we'll be basically using now, and that's basically where it comes from, and it's really it's a quick rule of thumb way to measure the cross section of a beam, right? I think I wonder if I'm gonna touch on that, but I'll probably touch on it afterwards. Over here is beam failure. So this I will not touch on now because this is not really part of what we need to do. But there's just some more background knowledge. Okay, so here we can start on a basic example. So I think I wanted to probably start with yeah, okay. So let's just follow the idea of the textbook here. And so we're going to start with example 10.1. And just to make you aware, if I'm going to ask this question, this typical question you're seeing is normally an add-on question, right? It's not a how do I say, it's one of the core questions, but it's normally an add-on question of what's happening. So how do we select the beam? And that's it. Basically, when we're selecting the beam, I feel there's a big jump in terms of content, but anyway, it's fine. How do we select the beam? Let's say the following criteria must govern the selection of the beams: the maximum bending moment, the maximum shear force, the width of the section, the cost of the beam, the maximum allowed deflection. The vertical axis must be the axis of symmetry. No, what is must have axis of symmetry. B must be light as possible. Probably the most important one, B must be light as possible. So what we're going to do now, we are going to select a beam, assuming we've done analysis. So this is the first example. So I'm going to look for the example quickly, right? So example, like I said, this is an add-on question. Doesn't really encapsulate what we're going to be trying to do. Yeah, we'll get there. I guess the first half of this lecture will just been me talking, and then we can actually start unpacking all the stuff. Okay, so I'm just looking for example 6.5 quickly. Just we all have a visual mind. We can actually start on example 6.5. 6.6, yeah. So just gonna snip him. He snipped. Oh, I don't want that. Okay, so example 6.5 is in your textbook, and it looks like this. And obviously, where this example initially starts. So, like I said, this is an important thing because you will get this as a sub question. Page 95. Thank you, Mr. Kasser. And if you do your shell force in penny moment diagrams, right? This is where it kind of runs onto. You're going to end up with something like this. So let me just quickly copy and paste this. So I'm gonna unpack this. It seems vague, but it's not. This is an add-on question. You start doing it properly now. But this is the way. I don't know why this chapter itself, the way it's set out. I don't know. I have an extra note which I use, and this one Panzer, which works out better. So initially we have our beam, and we do our shell force and bending moment analysis. And then we end up with this, right? So what's important here is to look for the maximum shell force and the maximum bending moment, sorry, because we're looking at bending, and the maximum bending moment occurred over here, right? And once you find the maximum bending moment, you can head off back to your formula over here. This formula is to do the section modulus. So now so what is the purpose of this question? They're saying choose a suitable I section for the beam in example 6.5, considering only one criteria 1 to 4, which is this criteria over here, right? So obviously, I ideally want to choose all the criteria, but anyway, just ignore that. So assuming a maximum bending stress of 100 megapascals. So what they're saying, we can't exceed 100 megapascals. Obviously, it's not within the elastic limit, but this is our working stress. Ignore the mass of the beam, and they say calculate the actual working stress and plot the stress distribution diagram for the section where the maximum bending moment occurs, right? So looking at the variables, we have the maximum bending stress, and also we have the moment, right? The maximum moment was given to us over here. So if you look at our formula, right? So Z is the section modulus. So if you're gonna look at the tables, the steel tables at the back, you're gonna see ZE where you see your I, E, and ZE, and it's the units times 10 to the power 3, right? 10(3). So you take your maximum stress. How do I change this, guys? Okay. So your maximum stress is 100 megapascals. Our maximum bending moment is 24.35 kilonewtons. And we divide it by ZE.
Did the book make a mistake, sir?
What?
Because in 10.1 they said the maximum bending moment is minus 24.85. You're using 24.35.
Let me have a look. Maybe I used the wrong example. Just check 6.5 quickly. It's probably me, man. Yeah, the example is 24.35. Yeah, okay. I'm looking and I'm thinking.
10.1 it says minus 24.85. Doesn't really make a difference to the answer. You still get the same answer.
Oh, I see. It's quite strange here. 24.85. Yeah. I wonder. But let's have a look anyway. Our ZT will be slightly off. Yeah, we can go with the book really. It makes no difference to me. We can go 24.85. Obviously, I think the book made a mistake here. And can I just get the ZE value? ZE is called a section modulus, by the way. I didn't say it properly.
That would be 243.5 times 10 to the minus 6.
Yeah, fantastic. 243.5 times 10 to the minus 6, right? Meters. I don't know, my thing is weird, man.
Yeah.
Yeah, okay. So what it essentially means, right? if you pull up your table, you need to find beams with properties close to that, steel tables. And they do actually talk about the procedure there. Steel tables. I don't have it here. Section tables, I call it. Section tables.
And sir, do you only look at ZE for the x-axis?
That's a good question. I'll check now. Moment. The state house bending here. Let me just read the question here. Yeah, let's call it for just call it for the x-axis for now. I will. Yeah, yes, it probably will be, because I'm looking at this beam over here, and if we're considering this beam as being bent, I'm just going to give it an arbitrary shape here. Oh, I need to shoot on my gravity tablet, guys. Sorry, man, really, it's not, you don't understand. It's just not doing what I want. Insert shape, man. Yeah, so obviously it's being bent across the x-axis. So yeah, in this case, the loads are all going down. So this should be the x. Just I don't know what's going on. Oh. X. Look, my hands look like I have a whiskey hand or something. That's not X, sorry. Just don't know what's going on. Okay, anyway, so obviously X is across the other side here. So we're looking at the X here. Anyway, okay. So I just want to get up my steel tables quickly here. So let's look at, I'm starting on, I don't want to spend too much time on this, obviously. I'm just showing you in the way the textbook is kind of moving along here. So we're looking at anything, any ZE column for the x-axis, right? So I'm starting on so I'm just gonna let me share the PDF with you. Okay. Like I said, there should definitely be a sub question within the textbook, so just be cognizant of that. I'm not shocked when you don't see it. Could be a good 4-mark question. Somewhere. Okay, and there's a few of these questions in your exercises. Now, guys, we're nearly ending the first session. We're gonna have a second session now. We have a small break. So if you look at the table, we're looking for ZE value of Alex was 243 something, right?
Yeah, 243.5.
243.5. So I'm looking at all these here, and this is all small, right? I don't know if you guys can see it. Maybe we should zoom it up a bit.
So it asks for a suitable I section, eh?
Yeah, but we have to look at the ZE.
Okay.
Oh, it tells us. Sorry. Oh, I should do. I was just kind of going through, like, showing you guys when. Anyway, it's fine. So obviously they want an I section. Thank you. But I'm just showing you. So for instance, what comes close on the L section or equal leg, we've got 235 there, right? That's not close. So no, we wanted 235. No, 245 or 243. So that's also not suitable. So obviously just scroll down to the I sections. I'm not going to waste time. And if you look at that, we could have chose 471. That is one candidate. 203. What's this? 203 by 5 and 2 by 52. But obviously, if we choose that one, it's way over what we require. I mean, obviously, and obviously, if you look at kilogram per meter, and we normally buy steel per meter, and that'll be an overkill, right? So we're gonna find something more closer. I'm just gonna check what answers they have here, just to kind of see. So out of chose, that's one correct answer, but that's obviously one option, right? So I'm gonna write it on my slides along as well, just to show you that there is other options as well.
So
Go for it.
The one that you chose, that means there would be a very high safety factor, correct?
No,
Is
it's just overkill. It's like an overkill, man. I wouldn't say high
okay.
safety factor. That's more like it's really it's more than what we need actually. It'll definitely. But the problem is, we look at the mass, the kilogram per meter is like 52, and
Okay.
yeah, it's just like an overkill thing. I'll just 2 or 3, anything higher basically. That's the idea. But you'll see now. But obviously, as engineers, we just don't choose. Obviously, it depends on how much money we have in the company and stuff. So I'm just choosing one section. I'm writing my next one now. Let's scroll. So that's 1. And over here is your H section, universal column, blah blah blah. And we're looking for anything close to 235. Yeah, we've got another one here, 274. So we could have obviously chosen all of these here. That would have been adequate. Your section modulus, but the 275 one seems a bit close. So it's 152 by 152 by 37. That's another one. So take that one. 152 by 152 by 37. What answers do they have? They have. Oh, they chose the same one I should have. Look, let me have a look. Okay. And then I don't even know which one is this. So the H section, right? That's the H. I can't see this cursor. Other one's an I section. Okay. Again, let's look at more. Let's look at more. So we won in the region of 270 something, right? Or 200 and something. This is now the parallel one, and I'm looking at my x-axis here. They all look massive here, right? So we could have taken this one as well, yeah. The 563.
The
That's also a bit too
203
much.
by 133 by 30 as well, you could take.
Which one was the Kessler? Just go back.
On your
Are you talking-
parallel flange for your I section,
Yeah, which one?
the bottom of the page, universal beams.
Universal beams.
Okay, like this little
This one.
bottom section called,
Little bot.
you know,
This
like
one.
it's on
Oh yeah,
the,
I'm with you. Yeah,
there,
got
then
it, got it.
203 by 133 by 30.
Yep, fantastic. Yeah, that's the other one.
Mm.
That's close enough, obviously. So 203 by what's it again? 203 by 133 by 30. Yeah. You want something higher, right? And so there's three sections you can choose, and if you're going to decide on which section to choose, Loam is to do the mass, right? And I think what they've decided to choose is the 203 by 152. What did they choose? Okay, anyway, I'll revert back. I'll see what they chose. Okay, so that's what we chose.
305 by 102 by 25. So
Is it the same as ours?
It's the 28. No, it's the 286. It's
Yeah,
the
so I don't
third
know.
from the bottom.
The third from the bottom. Is it in the same thing? Third from the bottom. Third from the bottom. So we have the 286 one here, right? This one over here.
Yeah, it's
Let's
286.
do
Yeah.
Okay, so 305 by 102 parallel flange. Okay, cool. So they chose this one. Okay, let me just. I'm gonna just cut this now. Okay, cool. Okay, now let me go back to the share. Share this. Yep. This is here. Okay, so this is just. So there's another section they chose, and that's gonna be Okay, obviously this. I don't know. There's also I section. There's H. So the H. Okay, they wanted I sections anyway. I just went for the H anyway, but you can choose something close. So they chose basically for this universal beam. They chose this guy, this one here, and they chose this one over here. Now I want to ask you, why do you think they chose the 305 section and not the 203 section? Equally would have been good with the section modulus. Didn't really make a difference. Who can tell me? Casso for Wormerlands. So going back here, you guys are a bit lost here. So criteria 1 to 4, eh?
Yes. So would it be the cost
for
of
it.
the beam?
Yes, but talk a bit more. Yes, cost. Why cost?
Cost, because you pay per meter of steel, I'm sure, at least per, well, for the quality
Yeah.
of steel anyway. So
Yeah. So
if you overshoot like the mark that you're supposed to be aiming for, it'll obviously cost more and it's unnecessary.
yeah, so basically what it is, I think what I'm looking for is that, remember that's just 25 kilogram per meter, that's 30, so that's 30 kilogram per meter, right? And the other one is 25 basically. So we have another section with 25 kilogram per meter, which is that there, and that is a better section model than that one over there. So we will rather opt for this one, because if we're going to choose that 30 kilogram per meter, obviously we don't know how much it really costs, because cost is, so we're looking for the lighter beam basically, and then that one's going to be lighter per meter, obviously 25 kilograms per meter, that's 30 kilograms per meter. So we're going for the one with the less M, arguably. So I hope you guys got that, right? So remember, the designation is HB times M for the beams.
I think there's somewhere, well, yeah, even example 10.1, so it even says that you're considering only criteria 1 and 4, so which is the maximum
Yeah.
bending moment and the as light as possible.
Yeah, sure. That's the thing, yeah. I mean, we could find out that the 203 by 133 cost by 30 cost cheaper than the 305, and that's possible because if you look at the manufacturing cost section is a bit bigger, so they even could be the same price. But obviously, we're just considering those four criteria. So anyway, you've chosen your section, the 286, and once you've done that, I can just add a new slide here. All you have to do is, don't have to compute this. So I'm going to say again, this is an extra type question. This is not, it's like a free form marks or something. But rest assured they do using beam design. It's like a quick calculation. Like, you know, rocks up on site. You know, we need to install this and that and that. You pull out this thing, you pull up your tables, you can do a quick calculation and check. Okay, yeah, let's go for this type of panel. Visual structure engineer guys actually do. And just quickly, there's a quick rule of thumb calculation which is helpful. I'm just going to copy the solution, so I don't have to now resketch the whole thing. So what you basically do is revert back to that formula. Oh yeah, so now we found ZE, right? And now we have to find, no man, don't do that. Okay, like this. We just basically go back to the formula. So we found ZE. From ZE, you can choose certain beams. Okay, they have different stuff they've chosen. Right? They selected a different parallel flange. Doesn't really make a difference to us. And then all you do is say your maximum moment again divided by that new section. In our case, it's 286 here. So ignore this here. This is the old Trotsky one. Yeah. So if you do that quickly, for our value, for our one, hey, I'm hearing sounds at Alex, Matthew, just muting me.
Oh, sorry, that's me, sir. Bye.
We just take our allowable stress. I think that was given as 100 megapascals, if I'm correct. We're looking at the new stress. So our moment was 24.35 kilonewton. And our new section is 286 times 10 to the power -6. And your new stress would be, I'm not sure exactly what it would be. Calculator. Obviously, the stress will decrease because we're choosing a bigger section here, so there won't be as much stress. I get 85. Yeah, stress has dropped drastically, but 35,1 for MPA. Obviously, because we have a bigger ZT, it's a better section modulus. Okay, so guys, what I recommend now, we're taking a 15-minute break. And then once we return, we're going to start on the normal computations, the ones what I expect to do, obviously. So try and do this problem. That's the first two problems in your textbook to choose the beams. Please go over it. You'll be a fool not to. So try 10.1, 10.2. Obviously, I have a few of them there. Not Alex did all of them. But this is a very important thing. At some point, you will be asked, maybe possibly in test 2, you will be asked choose a suitable section using this approach. So I'm just making you aware of what's going to happen there. Yeah. So now what I'm spending, around 2 weeks. Hopefully, it's one of those sections we want to spend a lot of time with. But it depends on how you guys do, obviously. Or now I'll explain as well. So do this too, and I'll meet you guys at past. I'm just counting how much. Oh, there's 7 of them. So let's see if we manage to solve all of them. All right. Okay. See you then. What's the door saying? Someone saying something. Do an example of density for sure. Which one would you like? The one that the example in the textbook.
No, not that one. It's just like, I think it's the first question after those questions. I'll show you now what I'm talking about. Huh?
The thermal beam one.
Yeah, I think with the density, 10.8, yeah.
Sweet. Don't worry, I'll sort it out. Yeah, so like I do not talk too much, but in the next section I'll start on a beam example, 2 basic beam examples, and I think after those 2, I can do that one for you, definitely. Yeah. So are we posting at least 3 extra notes on this chapter? So I'm just making it away. So please do this now. It's very basic, and then you start unpacking all the others. So I'm going to stop recording here for the first session, and then we're coming back for the next. But we have a bit of work today, so we have at least I'm pushing another 2 hours. I think, yeah. Cheers.